The complex plane is the geometric interpretation of complex numbers. Complex numbers are numbers in the form of z is equal to x plus yi. So something that has an imaginary number in it. And why this is getting brought up in polar coordinates will make more sense after I've just gone through this bit. So what's the complex plane? Complex plane, like I said, it's for graphing essentially complex numbers. And it works essentially exactly the same way the Cartesian plane does, which is used for solely real numbers. The complex plane has one real axis and one imaginary axis. And this makes sense. All of these numbers along the x-axis are real, and all of these ones on the y-axis are imaginary. So if I had z is equal to x plus 0i, this is z is equal to x, which is an entirely real number. There's no imaginary part to it, and that would only be along the x-axis. And similarly, if I had z is equal to 0x plus yi, then I get z is equal to yi, which is entirely imaginary, and that would only be along this y-axis. So graphing is pretty much the same thing. Try this, z is equal to 2 plus yi, something really simple. 2, 2, there you go, right there. Not any more complex than that. So why bring it up? Well, there are some annoyances with complex numbers, which is going to lead back into polar coordinates. So let me just show one thing. It's not really that annoying, but it's you'll have a look. Just look at this. So actually, this is a very common mistake that a lot of people make when first using the complex plane, because especially if they're just not really good at math, and then they're just not really thinking about it. They're just following whatever the book. They're just looking at the book's instructions and just following. They're not really actively thinking about what they're trying to do, what they have, and what they're trying to do. They're just operating mechanically, basically. So they'll use their distance formula, d is equal to square root of x plus y squared. And they'll just put this, let's just find the distance of this. This is z. So I'll do something like this. 2 squared plus 2i squared. And remember that I is equal to the square root of minus 1. So they'll probably do something like this. I squared plus, oh, I'm not adding anything. So I'll get I squared is equal to minus 1. And they'll continue, and they'll end up with something like this. So I'll do 2 squared is 4, I squared is minus 1. So minus 4 times, 4 times minus 1 is minus 4. That's what I was trying to get to. And they'll end up with something like 0. Which is obviously incorrect. This distance is not 0, obviously. But since they're dealing with complex numbers, not really thinking about it, they're just like, oh, complex numbers, they're weird. They probably have weird answers, and maybe an answer like that might put them off. But if these two weren't equal to each other, like if it was 2 and 3i or 2 and 4i, then you'd get something a bit different that if you have no idea what you're doing, you have no reason to think that it's wrong. But it's just really a notational issue. It's not really any different from the Cartesian plane. Most of the time, I'm just going to be ignoring the I in pretty much all mathematical situations. I'm going to be ignoring the I unless I'm getting an I times an I, which the I disappears. So unless the I disappears, it's really just a placeholder. It just sits along for the ride. It's not really that important. So let me go ahead and just show the notation for the distance formula in the complex plane. They use this notation, which looks like absolute value signs, but it's not really an absolute value. And it looks the same, and it is the same thing, really. They're just ignoring the I. See, z is equal to x plus yi. Well, I just ignore this I, and I just take the y value and I put it in there. And this is called the magnitude, or what was the other name for it? I think it was a modulus. Yeah, this is a modulus. So basically what I'm going to do is just my normal distance form is ignore the I. And this comes from, do I even want to bother with that? Yeah, why not? It's not an absolute value. I mean, it kind of is. I mean, I think it comes from the absolute value because you take the absolute value, it's the same thing as z times the conjugate of z, which is always going to be equal to x squared plus y squared. At least z times z. So then you get this. So just to show that z times the conjugate of z is equal to x squared plus y squared, I'll just do something generic. Just do x plus yi. So x squared, so that times that is x squared, and then this is going to be x, well, I already know they're going to cancel out, but let's just show x, oh, oops, well, I already know what's going to happen, so I did that part out of order. So that times that's x squared, that times that's x minus xyi, and this is going to be plus xyi, and then this is going to be minus y squared I squared, which is always going to be minus 1, which is going to change to this. So that's where that comes from. So it's clear that no matter what numbers are in there, it's always going to be x squared plus y squared. So that's where this comes from. And I guess really just getting back to what the whole point of this is the distance, right? So going back to polar coordinates are written in the form of r theta. So if I convert my complex numbers to polar coordinates, what I'm essentially going to do is have r, which is this distance, which is a real number. So this is a real number, and then theta is going to be a real number. So what I'm doing basically is just changing out of complex numbers and turning them into polar coordinates, or complex polar coordinates. Doesn't really matter. Basically the whole point is I've got r and theta, which I'm going to be using for my functional values that are going to be real numbers. So it's just less of a pain in the ass, basically. So that's the whole point. Eventually, the next few videos, whenever I do those, I'm going to be converting them to polar coordinates, and I haven't really personally used polar coordinates or seen imaginary numbers that much. Like I said, the only time I can ever remember seeing them or using them was in like particle physics or something like that. And that's exactly what it was. There was always this sign, sine, cosine, then I. And it was always in polar coordinates. I never really did them in Cartesian or rectangular coordinates. And I guess it makes sense because you don't want to deal with all this I crap, and it's just easier just to have r, which is, it's always going to be real, theta is always going to be real, and just you'll see once it's converted. It's just very easy to track the eyes and stuff like that. So I guess I agree with that kind of stuff. It makes a lot more sense to do it this way than to be with this other kind of stuff. It just seems easier.